Happy Monday, everybody. Welcome, Math 3000. It is not spring break yet, is it? Just making sure. Not yet. Seems like we're missing some folks, but that's okay. Glad that you're still here. We do have spring break next week, just in time for the end of the semester. We get spring break. That's really nice. So the plan for the rest of the semester, you've got one homework assignment that I added yesterday that is due when we come back after spring break on Monday. And then we'll have one more homework assignment that'll be due the last week of class. So you'll have two more homework assignments this semester, and then we have an exam on Monday of finals week. So our exam is scheduled according to the final schedule. Final schedule has us on Monday from 11 until 1. So finals are 2 hours long. I'll just tell you that our exam is not a final. Our exam is more like a midterm number 3. And it's not going to take 2 hours. So it's going to be the same as our previous 2 exams. So that's the plan. So we'll schedule it during finals week, but it's not going to be a final.
What day is the final, Adam?
It is Monday, May 10th.
Okay, cool.
I think that's the date. It's the Monday of finals week.
Thank you.
Yeah. Let me just double check the date. That is the 10th. Yeah, May 10th. So I put that, I updated exam 3, the date of that exam is too. So that's all up to date. Okay, so almost there. 2 homework assignments, exam, and then that's a wrap for Math 3000. So the plan for today is to, we started talking before the exam a little bit about, well, we did talk about partitions. You guys reviewed that today. And today we'll get into more into equivalence classes, how equivalence classes and partitions are related to each other, and then revisit some equivalence relations that we've considered and think about what those classes would look like and what sort of partition they might give us. But any other questions before we get going today? Okay. So last time we did talk about partitions. We talked a little bit about equivalence classes. So let's kind of pick up with that definition. So the equivalence class, so we have some relation, R, which is defined on some set S. And the equivalence class of some element A, which is in set S, would just be all of the elements in the set that it is related to by this relation A. And I'll just say, because equivalence relations are symmetric, it doesn't matter really where we put the X and the A over here. Okay. So if we want to revisit some of the stuff that I removed from the last homework assignment. So on the last homework assignment, you had to consider a relation R defined on the integers, which was saying 2 integers are going to be related if and only if their sum is an even number. And so you had to go through and verify that that was an equivalence relation. So I'll just kind of use that fact here, and let's just think about what the equivalence classes would look like. So first of all, right, we've got our set Z. So our elements are just going to be integers. So let's just start with the integer 0. So let's think about what the equivalence class for 0 would look like. So this would be the set of all things in all integers such that X is related to 0. And if we want to write out what that relation means, right, again, that relation is saying it would be the set of all things that when we add it to 0, we wind up with something even. So what would be some integers that would be in this set?
Any even integers.
Yeah, so for example, if I add 2 to 0, 0 plus 2 is 2, and that's even. If I add 4 to it, that works. If I add -2, -4, etc. Okay, it includes 0 itself. Again, it had better because this is an equivalence relation, so it should be reflexive. So there's an infinite number of things in here. So we can think about that as all of the even integers. So here's one equivalence class. Would be the equivalence class of 0. And we've got others. So now let's consider what the equivalence class for 1 would be. So this would be all of the integers x, such that when we added x to 1, we wind up with something even. So first of all, what we'll see in a second, we'll prove from this theorem, is that these equivalence classes form a partition, right? So remember, with a partition, the intersection of two sets should be the empty set. So if I'm thinking about this set, this equivalence class, it better not contain any of these elements, or else we have some problem here. But what would be some integers that would be in the equivalence class for 1? What are things that when I add to 1, I get something even?
Odd integers.
Yeah, so here would be everything else, basically, right? All the rest of the integers. So all the even stuff is equivalent to 0. All of the odd stuff right? So this would be all of the odd integers. Since adding any of those things to 1, sorry, I see I've got a delay. Since adding any of these odd integers to 1 would wind up with something that is even. Let me see. You guys can you hear me? Is it just my iPad that's delayed? Yeah. Let me share that again. Okay, so that was what I was trying to draw down below. Okay, so we have the equivalence class for 1 over here, which is all the odd stuff. So we could certainly just write that as all of the odd integers. So this relation partitions the integers into 2 equivalence classes here. I can write 1 as the set of the equivalence class of 0 and the equivalence class of 1. And again, there's nothing special about why I chose 0 or 1, right? I could pick any representative of element from those equivalence classes. So I could pick any even integer as my representative for the equivalence class of 0. I could pick any odd number for the equivalence class of odd things. So in other words, this equivalence relation creates a partition. We split the integers into the set of all odd stuff and the set of all even stuff. But one really important thing to keep in mind, there are a couple of things. Equivalence classes are, you know, they're pretty abstract things, and this is probably the first time you're coming into contact with them. So although we kind of use these square brackets, just be sure you're thinking about these things as sets. Okay, they are sets, so they contain a whole bunch of stuff. We just don't write all of the stuff here. It's a lot easier to write this than it is to write this. And that's why we make it a little bit more concise. So the one thing is these are sets. And the second thing is I could represent this equivalence class with any one of the things in that set. Okay, so there's nothing special about 1 here. I could have chosen 3 or -17 or any other representative. And the reason why is because this is reflexive, symmetric, and transitive. That's why it really doesn't matter which thing we pick. Okay, so any questions about that example of what we mean by equivalence, how we can represent equivalence classes for a given relation?
Does the symbol inside of the brackets have to necessarily be one of the elements in the set, or can it be the equivalence class A that represents this set of integers or etc.?
So the representative that you choose has to be one of the elements in the set. Yeah, so this is just done in general up here when we did the definition. There, A, but A would be one of the elements in the set. So I mean, it might not be a number because the elements might not be numbers, but it should be some element from the set S.
Okay, thank you.
Okay, I'm gonna just cut this stuff out and put it on a fresh page since I want to prove this thing. Okay, so a couple of theorems. Some of them we'll go through. I'll go through this one together a little carefully, and then the others I can kind of just walk us through the proofs. But the main point today is to get to relations and think about relations we've considered and what equivalence classes we would get out of those relations. This kind of first thing is really saying that it doesn't matter which element from the equivalence class we pick to be the representative. So this is really saying 1 and -17, they were related to each other by the previous relation. So I could have represented that equivalence class with 1, or I could have represented that equivalence class with 17, -17. So when we were talking about this example, we would say that the equivalence class for 1 is equal to the equivalence class for -17, since 1 is related to -17. I see we've got a delay again. Let's see how long it is. Yeah, sorry. I was trying to just kind of connect that previous statement back to saying, because 1 and 17 were related to each other by this sum is even relation, that the equivalence class of 1 is going to equal the equivalence class of 17. They're both going to be related to every other odd integer. So that's what this theorem is saying on the previous page.
Question for you.
Yep.
When you're trying to determine all of the equivalence classes of a relation, when you can prove that all of the equivalence classes make up a partition, does that prove that you've met all of the equivalence classes of that relation?
Yes.
Okay.
Yes. So we'll see today that we could really use these terms interchangeably, and we do all the time in mathematics, whether we call something an equivalence class or whether we call it a partition. They're really essentially the same thing. So we can think of equivalence classes as special types of partitions. Any partition we can think of as an equivalence class, so it goes back and forth. Okay. So let's see. I hope I can write without too bad of a delay on this. So let's consider the following theorem. So this theorem is basically saying that if we have, if two things are related, then their equivalence classes should be equal to each other. That's what this is saying. And this is an if and only if. Okay, I am writing here, but this is kind of slow. Okay. Okay, this is kind of unpredictable. Let's see. Sometimes it takes a while. Sometimes it's a bit delayed. So we'll see. Okay, so let's take a look at this. So basically, all we want to say is that if two equivalence classes are equal, then their representatives should be related to each other. And if two things are related to each other, then their equivalence classes are equal. So it's an if and only if. So we've got two directions to prove here. So we'll first take the forward direction, which is saying if equivalence class A equals equivalence class B, then A is related to B. And then we'll do the reverse direction. So we'll do this one by direct proof. I think I'm okay writing. I think I just get delays when I scroll around. Okay, so good. So let's, first of all, let's let A and B, these guys should be elements in our set S. And since we're doing this directly, we are going to suppose that their equivalence classes are equal. And now what we're hoping to show is that they're going to be related to each other. Okay, so let's consider, and remember, these are sets. So when I say equivalence class A is equal to equivalence class B, I'm really saying, right, that set of values is going to contain all of the same elements that equivalence class B contains. So let's consider some element X, which is in equivalence class A, excuse me. Then we know that X is related to A by definition of equivalence class. And since we assumed that these two equivalence classes were equal to each other, if X is in the equivalence class A and equivalence class A equals equivalence class B, then X should also be in equivalence class B. So this tells us that X is related to B. And recall, right, what we're hoping to show here, if we're going to prove this direction, is we want to show that A is related to B. So what we know is R is an equivalence relation. And we've got this fact over here, and we have this fact over here. We want to try and prove this. Any thoughts on how we can connect these pieces? So R is an equivalence relation, right? What are the
Transitive?
So we're going to use a transitive property. Seems like it would be useful here, but we need to be a little bit careful, right? The transitive property in general says something like if X is related to Y and Y is related to Z, then this tells us that X is related to Z in general. That's how transitive property works. And so, right, it's saying that, okay, on one, we have X is related to Y, and then we're going to say that this Y is related to something else. So yeah, we kind of have that stuff. We want to get this. So kind of, what do you think should go in these blanks if I want to use the transitive property to prove that A is related to B? So what would make sense to put over here? B, thank you. What makes sense to go in that spot then?
X.
Put an X over here, and then what should go over here?
Symmetric property on the first one.
That's right. So we're almost in that position, but not exactly right. Okay, but you can see that if I knew A was related to X, and then I also know that X is related to B, which I do have that up here, then that would get us to A being related to B using the transitive property that I know R has to satisfy, because we are told that R is an equivalence relation. That's right. And I don't have this, so we really need to be careful about things. I don't technically have this. I have X is related to A, but now we can use the symmetric property of the relation to get the other order around. So let's kind of summarize that. So since, let me just move this down. So that tells us why we can switch the order around. And since it's an equivalence relation, it is also transitive. And so since we've got A is related to X and X is related to B, then by the transitive property of R, that gives us A is related to B. Okay, any questions about that? Okay, so this tells us if two equivalence classes are equal to each other, then the representatives of those classes have to be related to each other. That's what we're getting from that direction. Okay, then let's take a look at the reverse direction. Again, you know, labeling these directions really helpful. Okay, so for this direction, now we want to show that if A is related to B, then their equivalence classes are equal to each other. And just kind of a note here is that equivalence classes are sets. And so if I want to prove that these are equal to each other, I need to show that this thing is contained in there and that this thing is contained in there. And then those two sets are equal. So I'm hoping to show that anything that's in the equivalence class of A should be in the equivalence class of B and vice versa. And so if you kind of think about what these equivalence class properties are, right, really what we're trying to show is that anything in the equivalence class of A, so that would be anything related to A, also should be related to B, should be the equivalence class B. And what's important here is that we know we're assuming that A and B are related. So there should be some transitive property stuff going on around here, I would suspect as well. And that's why we see that these properties are quite useful, why we're interested in these three specific properties, reflexive, symmetric, and transitive. These are the properties that we need in these proofs. Okay, so in this direction, we're also going to do this directly. So let's suppose we have two elements A and B in set S with A related to B. Now we're going to try and show that their equivalence classes are equal. So let me first think about doing it this way. So if I want to show that equivalence class A is a subset of equivalence class B, I take some element that's in equivalence class A, call it X, and we want to show that that element has to also be in equivalence class B. Once I know anything in equivalence class A is in equivalence class B, that's going to tell us that part. Okay, so we've got some element X, which is in equivalence class A. Then we know that X, by definition of equivalence class, should be related to A. And again, what we're hoping to show is that X is in equivalence class B. So I'm hoping to show that, right, that would be showing that X is in equivalence class B, if I can show that X is related to B. So I've got this I know, this we know, and we're hoping to show X is related to B. How can I connect those things to show that X should be related to B?
So if X is related to A, we know that A is related to B, and by the transitive property, B would also be related to X.
Yep, that's right. So a transitive property here, and we actually don't need to finagle anything around. It's already set up like that. So I know that X is related to A is related to B. That's going to tell me X is related to B. But as I'm writing this proof, notice I'm telling the reader like exactly what properties I'm using of the equivalence relation. So be specific. Don't just say because it's an equivalence relation, we know X should be related to B. Explain what about the equivalence relation is leading to that connection. So here we're using the transitive property of this relation R. Since we've got X is related to A, and A is related to B, then X is related to B. So this tells us X, therefore, is in equivalence class B, and that proves that A is a subset of B. Equivalence class A is a subset of equivalence class B. I'll just put in blue here. Similarly, we could show that equivalence class B is a subset of A using the same sort of argument here. It would be good maybe for you just to verify how that would go. But rather than starting with something in A, we would let's consider some element Y, which is in the equivalence class of B, and then show that Y has to be in the equivalence class of A. So once we got both of those directions, this would tell us if A and B are related, then their equivalence classes are equal to each other. And that proves that result. So this is really getting at why these properties of equivalence relations, why these three properties were really nice, is they give us nice, well-defined equivalence classes. If two things are related, then their equivalence classes are related. Any questions? Okay. Okay, then we did talk about partitions last time. So this is notes from last time. This was notes from last time. Okay, so now just want to quickly go through the outline or go through the proof here. This is in the textbook. This is Theorem 11.2 in case you're curious about it. But what this is saying is the set of equivalence classes resulting from an equivalence relation gives us a partition on S. That's really saying any equivalence relation on a set leads to a partition on the set where each part is in a different equivalence class. So let's just kind of go through the proof here. So again, what we're trying to show, if you think about a partition, I had it on the previous slide, but this means that each part is non-empty. We have the intersection of any two parts is empty. One of the conditions was they're mutually disjoint. And the last one was the union of all parts gives the entire set. So we're going to check that equivalence classes satisfy these conditions. That's the goal here. Okay, so okay, first thing to note is that there are no empty sets, okay, when it comes to equivalence classes, because for any element in the set, it's related to itself. So that means there are no empty set equivalence relations. So over here, we're using this reflexive property is important here. So let me just say that that first part being non-empty, that comes from the reflexive property of equivalence relations. Great. Any questions about that? All right, so then next let's think about showing why these equivalence classes are disjoint from each other. That's the next property. Okay, so now we've got any element A has to be in its own equivalence class because of the reflexive property. So that means every element of S appears in some part of P. So that means, I guess, sorry, I'm skipping down to the last property. So this is going to tell us that if we take the union of all of these equivalence classes, we are going to get back the entire set S back, since each element is going to be in its own equivalence class. So every element is going to be accounted for. So both of those things really come from the reflexive property, I should say. Okay, and so now what we want to show is that if we have two different equivalence classes, they can't contain any elements in common, so that they're disjoint from each other. So let's consider two elements A and B that are in different, that have different equivalence classes. Okay, so in other words, we're going to assume here are two elements A and B that are not related to each other by relation R. So here, this third part here, we're kind of proving by a contradiction in some sense, right? So if we assume the opposite, that they do share something in common, then what we see is there would be some element in the set which is in both of those equivalence classes. And using symmetric property and the transitive property, this would lead to a contradiction here that A is related to B. So that gives us our contradiction. I think I said contrapositive here. Sorry, I meant contradiction. So therefore, they have to be disjoint. And that proves the last property. So these symmetric, reflexive, transitive, first of all, they tell us that these equivalence classes are nicely well defined. Secondly, they actually give us a partition of the set. Any questions about that?
Was that kind of like the proof to show that a partition is an equivalence class? Like, is equivalence relation? Like, are those two?
So this told us that any equivalence relation gives a partition, and kind of the next part is to show why any partition would lead to an equivalence relation, and then we get that equivalence relations and partitions are the same thing.
Gotcha.
And the proof is pretty similar. And again, I think if you guys are following along with the proof and just taking some side notes, that should be sufficient. I wouldn't ask you guys to prove these theorems, but we're going to apply them shortly. Yeah. So now what we're going to do is say, okay, let's start with if we have a partition. Why is that going to give us a relation? So we're going to define from a partition, we're going to define a relation R to say that two things are going to be related to each other if they are in the same part. And so the claim here is, let's prove that this is an equivalence relation. And moreover, that the equivalence classes are actually the parts of P. So we kind of went the other direction previously. We said any equivalence relation gives us a partition. Now we're going to say any partition, we can define an equivalence relation. So we need to show that it's going to satisfy reflexive, symmetric, and transit properties. So first we'll show it's an equivalence relation, and then we'll worry about this part about the equivalence classes being the parts. So if we want to prove that this relation that we just defined, and again, the relation that we're dealing with is this one over here. So we have some partition of the set S. We'll call those parts, and then we're going to say, each of those P's are some set of things. So we're going to say that elements are related if they fall in the same part. Okay, so first we want to show that this would be reflexive, and that usually is a pretty quick proof here. I think I left out a word. I want to have same in here. So we take some element A, which is in the set. A is in the same partition as itself. So therefore, by this definition, A is related to itself. There's our reflexive. Any questions about that one? Usually the reflexive property proof is really quick to show or disprove. Okay, so then let's kind of move on to the symmetric property, which would say, okay, if A is related to B, then why would B be related to A? Also a pretty quick argument here, right? If A is related to B, by this definition, they're in the same part. And if A is in the same part of B, then B is in the same part of A, thus symmetric. And then for the transitive property, we would take three elements. We're going to assume A is related to B, and then B is related to C. Yeah, hopefully this is also pretty quickly follows that if A is in the same set of B and B is in the same part of C, then A and C should be in the same part. And that gives us the transitive property. Sorry. So that tells us R is an equivalence class, or excuse me, an equivalence relation, since we've got those three properties satisfied. And then the last part would be, yeah, maybe I'll kind of just leave this for you guys to verify. But then the last part here is just arguing that each of the equivalence classes of this relation is actually leading back to one of the original parts of the partition. Mostly want to make sure we're clear that why these partitions, in fact, give us nice equivalence relations from those properties. Okay, so the big takeaway from these theorems here if I have an equivalence relation on a set, that gives me a partition. If I have a partition on a set, that gives me an equivalence relation. So we're really talking about the same thing at the end of the day. Okay, so any questions about the theory before we take a look at some examples together? Okay, so we did 3 on the previous page. So we're just going to come back and finish up the homework assignment that you guys weren't able to finish last time, where there were some questions about, hey, tell me what the equivalence classes would look like for these relations. So I'll just say I did finish grading your exams. I will post those grades up after class. I figured you were more curious about how you did on the exam than on homework 8. So I haven't graded your homework 8 yet, but I will get to that. But on that homework assignment, one of the questions was, we're going to let F denote the set of all differentiable functions. And the relation D was saying 2 functions are related if and only if they have the same derivative. And you guys had to prove this was reflexive, symmetric, and transitive, which it is. So then let's consider what some of the equivalence classes would look like for this. And now we don't have numbers as our elements, right? We have differentiable functions. So I don't know, let's pick the equivalence class for x squared. So by definition, it's going to equal the set of all functions such that f is related to x squared. So in other words, it's going to be the set of all differentiable functions so that the derivative of f is equal to the derivative of x squared. So what's one element other than, say, x squared that would be in this set? Can you guys think of another function that has the same derivative as x squared?
X squared plus 2.
Yeah, so x squared plus 2, x squared minus 18, so on, right? So these are going to be all things really right? Anything that looks like x squared plus a constant. So, right, we can't write out all of these equivalence classes like we could with the even and odd example because, right, we've got an infinite number of equivalence classes, but in general, right, given any function g, right, is going to look like any thing that differs from g by a constant. So that's one way we could describe the equivalence classes that we get here. So this is a large set, the set of all differentiable functions, huge. So we have an infinite number of equivalence classes, each with an infinite number of elements. here, elements would be differentiable functions. Okay, any questions?
I have a quick question.
Yeah.
Quantitatively, will we say there's only one equivalence class, or will we say there's infinite?
There's an infinite number of equivalence
There's
classes.
infinite? Okay.
Yeah. So you can imagine, like, even if we just think about polynomials and not even thinking about other functions, right? We have, there's an equivalence class for constants. There's an equivalence class for x plus constant, x squared plus constant, x cubed, right? So there's tons and tons of these equivalence classes. So here I just wrote one just to say, like, given any function, its equivalence class would be all of the functions that differ from it by a constant.
Okay, thank you.
Yep. Okay. So yeah, so here we did that one. The other equivalence relation that was on that previous homework assignment, you had a relation C on R2 on the Cartesian plane, which said if I take an ordered pair x, y, it's going to be related to some other pair uv if x squared plus y squared is equal to u squared plus v squared. And if you're ever kind of stuck about like what to do as far as how can I start to write out some of these equivalence relations, I think if you're stuck, just pick a concrete example and pick one that's not so bad. So if I want to think about what are all of the ordered pairs that are related to 1, 0, it's going to be all of the things uv such that u squared plus v squared is equal to 1 in this case, right? Since that's what x squared plus y squared is. Does anyone have a better description of what those things would look like? What this equivalence class would look like? What does that thing look like if you were to graph that in R2? The set of ordered pairs that satisfy the sum of the squares of their terms is 1.
A circle?
Yeah, that would be like a circle radius 1. Yeah, I mean, that's pretty much what I've highlighted there, right? So this would be like a circle. So on, right? So basically our equivalence classes, we have this plane R2, and given any point, I don't know why I need to pick it on the axis. Given any point xy, I just calculate what is the distance of this point to the origin, and then any other point that's supposed to be a circle there. When I'm teaching trig, I get really good at drawing circles. I'm out of practice. Any other point on that circle would be related to xy. So in this case, our equivalence classes are circles in the plane. So it's nice. Sometimes we get these nice geometric interpretations of what the partitions might look like. And then you can see that, yeah, this matches. I could partition the entire plane by thinking just by putting a bunch of concentric circles going out. That would, every point is on some circle, and each point can't be on more than one circle. We get a partition. And we have one really special equivalence class. which is the origin, which just contains itself, right? That's just an equivalence class of one element. All of the rest of them would be circles. Okay. So gonna break us up into rooms and have you guys think about some of these other ones. And maybe let's start with an A and then let's go to a B. Someone escaped real quickly when I said we're gonna go to breakout rooms. You're not forced to come to Zoom or go to breakout rooms, but your cooperation is appreciated. So let's think about A and B maybe. Let's start with those. And on homework, you're definitely going to have to do some stuff with some modular equivalence relations. And if you are, happy with getting through A and B, then you can think about some of the others. But maybe let's take, let's see, it's about 11:55. So maybe let's take about 10 minutes of thinking about things in groups. And then we'll come back together and touch base on them. But any questions before I break us up to groups? Welcome back, everybody. I think now you can hear me. Okay, so yeah, I want to make sure that you guys had some chance to think about how these equivalence classes work. You've got a homework problem on this due next time. And these are really fundamental. Equivalence relations classes are a really fundamental thing if in like number theory or some other disciplines in mathematics. So in A, kind of the group that I was working with, they came up with the partitions here would be even and odd integers. Were there any questions about that? So there are different ways that we can write these sets out. I just also want to make sure that we're comfortable, like we can use the equivalence class notation. I can be a little bit informal like this. And it's a pretty nice set builder notation way of describing what these sets would look like without having to list all of the elements. So one thing to notice is that this relationship over here, the same parity relation, is the same thing as the x related to y if and only if x plus y is even relationship. So they give us the same partition in the end, so we would consider these two relations equivalent. Okay, for the mod n relation, our group, we struggled with that, I think. And so we tried picking an integer to work with rather than n. We said, let's think about 5. Yeah, and so if we were thinking about this relation, and we're just so you know, we're at 12:15. So if you need to run, that's okay. The tape is rolling here. I think we'll just need another couple minutes to complete this. So if you think about the relation A is related to B if they're congruent mod 5. And then we can think about what the equivalence classes for this would look like. And so we kind of started with, well, let's think about the equivalence class for 0. So by definition, that would be the set of all integers related to 0 by this relation. So it's going to be all of the integers such that x is congruent to 0 mod 5. So I'm just kind of writing out different ways that we could express this. Okay, and so one way to think about the modular congruence would be two things are congruent mod 5 if their difference is divisible by 5. Okay, and another way to say that is it's all things that are multiples of 5, right? That have a remainder of 0 when we divide it by 5. Right, so we could write that as 0, 5, 10, 15, so on. And we also are including all of the integers, so these could be negative things as well. So this is kind of plus or minus, plus or minus, plus or minus, since all of those numbers are divisible by 5. So in other words, we could write that as the set of all things that are multiples of 5, right? Okay, and so in that sense, right, I could choose equivalent representative 0 to represent that class. I could choose 5. I could choose 50, right? We could pick anything from that equivalence class, and I'll just say we typically use 0 as a representative of that class. Any questions? Okay, then we can think about the equivalence class 1, which would be all of these integers such that x is related to 1. And kind of using this logic, it would be the set of all integers such that x minus 1, right, is divisible by 5. So in other words, we can think about that as all of the integers which are of the form 5k plus 1. So for example, 1 would be in there, right? The next number would be 6 and 11. And so what you're seeing is, right, every time I add 5 to the representative, I'm getting another element in that set. And by the same token, anytime I subtract 5, I should get, so adding and subtracting multiples of 5 is going to give me things in this equivalence class. So I could take 1 and go 5 below that, and that puts me at -4 and -9 and so on. So basically all this is saying is we take our representative 1 and then we're adding and subtracting multiples of 5. And again, you know, whether I choose 1 as the representative of this class or whether I choose 6 or 11, right, they would be the same set. So just to kind of summarize this for the situation for 5, right, we would have 5 different equivalence classes like this. This would be the set of all things that are multiples of 5. These are all the things that have remainder 1 when we divide by 5 and so on. And that's it, right? I don't need to think about the equivalence class for 5 because that's equivalent to this one. And I don't need to think about the equivalence class for 6 because that's equivalent to this one. So in the end, that gives us, partition the integers into 5 equivalence classes for 0, 1, 2, 3, and 4. So I hope that, from this, you guys kind of see a blueprint what to do if instead of 5, we chose 6 or 7, or if we just let n be an arbitrary integer, how that would work. Okay, so I definitely have to stop here. We've gone over, so thanks for that. So yeah, got our reading quiz. So this wraps up the material on equivalence relations. So the reading quiz for Wednesday is just going to really review the idea of what it meant for a function. What is a function? What is the domain, range? What does it mean to be injective? We talked about that earlier in the semester. And then we'll build off of that on Wednesday, talking about surjectivity and possibly invertibility and things like that. Okay, so homework is up. You guys can get going on a good chunk of that if you would like to. Some of this stuff about is this injective and surjective we'll talk about on Wednesday. And that homework is due after the break. So you've got spring break to work on that if you like, or finish it before spring break and actually take a break, whatever you prefer. Okay, thanks everybody. I will see you guys on Wednesday, unless you have questions. I've got office hours tomorrow. Otherwise, see you guys on Wednesday.